Babu. I've done a PhD from NIT Oral Development. I'm currently Associate Professor in the Department of Mechatronics and Multimodal, and also I'm co-founder and director for SQL Novatech, which is working on energy and biometric devices. So this is what about me. I'm also a research collaborator with NIT Oral in India to see MSRD project on reluctance models. And I'm also faculty advisor here for Solar Mobile, which is working on electric vehicles student major project. It is based solar-based electric vehicles. We are working on that. I'm also co-coordinator for Center of Excellence E-Mobility MIT Manipal. That's brief about me. And I hope that sir has already started the session on switcher reluctance machine. And I try to brief a couple of things which are necessary for me for modeling and control of SRM. Then a little bit on SRM advantages and potential in EV. So we will see that, and as well as we will continue with doing some model exercise. First we will try to do some model to understand it more. So basically we will try to understand the principle of control strategy in the reluctance motor, and that's what we will try to do. Now, switcher reluctance machine, we'll see a brief on control construction picture. Quickly I'll go through that because already points should be covered. So, I try to look to which is necessary for me. So, as we all know, reluctance motor work on principle of coil and silicon steel. So, we know three combination of motors can be classified into these three categories. It can be with a coil, or coil magnet and coil steel. So coil, we know very well induction motors works on principle of induction principle where induced EMF is going to contribute for the motion. And in case of permanent magnets, we know very well permanent magnets will contribute to the motion with the coil. And the other possibility of is having coil and a piece of iron. So when we excite the coil, the iron tends to move. So this principle is called as reluctance principle. So, as we know very well, as might have already discussed, due to larger air gap is larger, you have, when it's unaligned position, you have larger air gap that results to a larger high reluctance. So, high reluctance is high at this point. And when we exit this space, the rotor tends to move, and we have a smaller air gap, results into smaller reluctance or low reluctance. So this tendency of moving from high reluctance to low reluctance path is called as reluctance torque. And we know very well there is no coil on it, or there is no magnet on it. This has been already discussed. Now I want to look at this aspect of reluctance. When there is high reluctance, okay, so we need magnetic saturation will be linear, whereas when it's low reluctance, we have more fringing or effect, or saturation is very high. So this is why I'm not covering that much part of that in detail. And in this key aspect is that for variable speed drive, we can see that it is very good to see that reluctance motors are more promising. And we know very well EVs are EV themselves are variable speed drives. And even autoporting application is also variable speed drive. So that's the reason in this aspect it stands very good. That's called some flat over efficiency. Possibly we will see somewhere some results are regarding to that one. Flat over efficiency in the sense you have more, for more speed range you should have more high efficiency. So this is omega, this is efficiency, this is flat over efficiency. Induction motors have the problem of low efficiency. In the sense when speed is low, efficiency falls down. And for permanent magnets, it's intermediate. Those are good in peak. Peak efficiency is high permanent magnet, but they are not for over the speed range. They are not contributing into the efficiency. So that's the reason it has a very good potential, and people are looking for switcher reluctance motor drive in this case. A couple of other advantages. For our instance, as I told you, when it is unaligned position, due to reluctance, the inductance will be low. You can see the slope will be linear, and the slope of this one indicates the inductance value, and it will be low, and that's the reason you can see at unaligned position low inductance value. And as it moves to saturation, when it reaches to this position, you have saturated inductance, that is aligned inductance value, and that aligned inductance value will be high. And as it moves from this side to this side, we have again the falling of this one. So this is very essential part to learn, because it will help us to control. Yes, sir. Okay. So very essential part. So I want to highlight on this. So this is very brief about them, though it might be covered, but for us it is very essential to look into this. Now, when it comes to the governing equation, any magnetic circuit or magnetic coil, we have voltage is equal to R into I d psi by dt, where d psi this is the flux component, okay, in reverter. So if we rearrange for this equation, the flux will be V minus IR into dt. So this becomes very crucial thing in our thing. Now, why we are looking into this one is that though in our previous slide, what we have seen is that so unaligned inductance and aligned inductance, we can see rise of the thing. And most of the magnetics properties, if you don't consider this saturation, will give you inaccuracies. So if you don't consider, most models, what happens is that they will try to put all the lines in a linear way. So they is called as linear models. Now, linear models have the problem of inaccuracies. In order to sort out this linear modeling, so we have to consider non-linear characteristics of this. Non-linear characteristics. And you can see, if you consider the saturated profile, then it will be a non-linear characteristics, and because of that one, you have high accurate model. Okay? So that's the reason going into this flux is very, very essential. And if you consider only linear model, flux is equal to L into I, okay? And that's the reason we have voltage equation V is equal to R into I plus d psi by dt. If you put that linear into the characteristics, generally we know voltage equation can be written I into R plus L di by dt. Now, because L di by dt is only considered good and accurate only when it is a linear characteristics. But when it is non-linear characteristics, instead of considering this linear relation, we have to consider only flux. So the actual equation becomes V is equal to R into I plus d psi by dt. Now getting this flux is very important for us, and that's the reason if you arrange flux is equal to rearrange this equation, and if you rearrange that equation, we can d psi by dt becomes V minus I into R. Okay, and if you consider that one, if you put integration to both sides, then final equation will become this flux is equal to integration of V minus I into R dt. So this will help us to go inside accurately to get into the flux. Okay, and from flux the co-energy is computed, and the co-energy from co-energy principle we can compute the torque required, and torque equation so is given by I square by 2 dl by dt. Now the other way of putting it is that since flux is not a linear, it's a non-linear characteristic. That's the reason we have N into I, and derivatives of that one will result finally. We can see that this is the energy stored, derivative of the energy stored in the inductor, and the power that is going to the shaft. So when it's going to the mechanical power is this one. So finally this into this. This is torque into omega is the power that is going to the shaft. So this is mechanical output. So this equation, when we correlate, so again the equation we will say that is I square by 2 dl by d theta. Now, to the beginners or any other one who are new to this line or anything, if you understand this equation, it is very essential, it is sufficient information for us to understand the control strategy. Now, I square by 2 we will discuss in detail, and that's the reason we are working on dl by d theta. So, we need this inductance slope for the control strategies to understand. Now, proceeding on to that characteristic, you can see it here. Now, let's learn to this equation itself. And what we can see is that if you want to have positive torque, okay, the only means that it is not independent on the current. For example, if I change the direction of the current, since it's minus I square, results again into I square. So this I will not contribute, I is not at all contributing to the sign. Okay, so if you want positive torque. Now, whereas this sign is dependent on the slope of dl by d theta. Okay, and if you want positive t, that means you need to have positive dl by d theta. And this is nothing but the slope of inductance. Okay, and we have seen that from unaligned position to aligned position, the slope is rising. So here in this region, slope is positive dl by d theta. And if you want negative torque, the only means in this equation, that is, you have to continue to do written dl by d theta, minus dl by theta, which is nothing but slope is decreasing. So this is minus dl by d theta region. So this positive torque, we know very well, positive torque means it is nothing but motoring mode. Okay. And the negative torque is nothing but typically generating. I hope this information is very a simplified way to understand principle. In a way that you want to have motor mode, you want to accelerate in motor mode, all you have to do is that you have to switch on the phases when there's positive slope of inductance. In this region, we need to turn on. So, I'm just turning on in this region the coil. When we excite in this positive slope of inductance, then we will get motoring. The same thing when we switch on into the negative slope region, okay, then we will get into generating mode. So this is very essential, switching from positive slope to negative slope. And let us take a case of 8 by 6 SRM. So where 8 is stator poles and 6 is rotor poles. And with that, what happens is that if you have 360 degrees total angle, and the slope of the positive to negative slope of dl by d theta will comes to be divided by the rotor phase comes to be 60 degrees. So this 60 degrees indicates entire one cycle of that pole. So what we can see as we go back. So this position, if you consider nominative or if you take it as 0 degree, that means this entire degrees span is 60 degrees. And within the 60 from 0 to 30 degree, it will be positive dl by d theta, and from 30 to 60 degree, it will be minus dl by d theta. Okay. Now, if you want to have motoring mode, all you have to turn on or excite the phase in this region. So when the rotor is in this region, okay, in this region, positive slope of inductance, then you excite the phase. So that will give you the motoring mode. And the same thing if you switch on, excite the phase or excite the phase and tap the generating mode of energy. So there, what we have to switch on between minus dl by d theta position. So between these positions. So this is the way switching has to be carried out. Now, we understood that positive and negative sign of this one is on dl by d theta, where we switch on, where we switch off. Now, other important point that you have to learn for any application is that what is the magnitude of this torque, how I can increase or decrease. So the means that we can do here is that it is not depending on dl by d theta, but we can see the magnitude is dependent on I square. Okay, so the magnitude of the torque is dependent on current. So since it is I square, for example, in this case you just double the current, you will get 4 times the rated torque. So if this I is rated and we have rated torque on that road, so if you double the rated current, then we have typically from this equation we can see we can have 4 times rated torque. This is very one of the essential part of reluctance motors principles. So if this is the current, and if I am turning on and turn off with a positive slope, that means I am motoring in this region, and the magnitude of this one, the magnitude of the current will decide the torque magnitude. Okay. So these 3 parameters are very, very crucial points to learn. Is that when I am turning on and when I am turning off, and which region I am turning on and turning off, and also the magnitude of current. Okay. Now, the good point about the reluctance motors is that since it starts proportional to square of the current, okay, this is very good for starting acceleration, where you want to have higher torque. With a small minimal change in current or doubling the current, you can have 4 times the rated torque. That's what we can see. Which was in older versions of the electric motors. In the older versions of the electric motor, the old motor that was contributing to this one was a series motor, DC series motor. So DC series motor was also proportional to square of the current. The challenge in DC series motor was, though it was giving 4 times rated torque because of the current doubling, though it's the same equation related to that the torque is proportional to square of the current, but the challenges that we face in DC is that we have effects of brushes and sparks and maintenance issues. So because of all these things, the DC motors, series motors were very challenging, and that was old, and nowadays nobody we are using DC series motor. But in the current trend of motors, which can contribute to this the torque is proportional to I square motor, you can see here clearly, reluctance motor will help us. And the counterfeit of this one is that in this case, reluctance motor are producing 4 times rated torque, but I think so since it's a laminated steel core within the one, so easily you can get into current to I square R, and there is no problem with the brushes, and there is no challenge of sparks and all that, no maintenance issue. So that means it's the same property of the series motor which we can get in a better way in reluctance motor. So this is another key factor which is being currently used for in EV applications and everything also. So in a nutshell, if at all we can consider the magnitude of the torque is related to the current magnitude, the magnitude of the current, and the sign of the torque, positive or negative, is dependent on dl by d theta. So if we understand this base principle, I think so we can understand the basic control strategy of reluctance motors. So we'll try to learn one by one parameters and try to consolidate that. So these are the 3 parameters which are essential to control the reluctance motor drives. Now when it comes to control, okay, so there is a 2 way of understanding the principle here. So I want to look into this characteristic itself again. We can see it is that when the inductance is low, okay, and a basic inductance equation, voltage equation of any inductor is that L di by dt. So what happens when inductance is low? It's a low inductance. Okay, and when you do low inductance and when we have a full voltage applied to the coil, okay. So when we have full voltage applied to the coil, full voltage of VDC, higher voltage of VDC. So full DC voltage, DC converter topology method. When we apply high voltage to that one, what happens is that because of high voltage and low inductance value, what we can see is that rise of current will be very, very high. And any motor equation we know very well, VDC applied is equal to R into I plus L di by dt or any back EMF component. Now back EMF component we know very well, this is dependent on speed. Okay. Now when the motor is at start, when the motor is at very low speed region, so when we say low speed region, okay, at low speed region what happens is that back EMF will be very low or negligible. So there won't be back EMF in low speed. So when there is no back EMF in this, and this is very small drop because resistance is very small current. So at low speed what happens is that the applied DC is nothing but it becomes L di by dt. Okay, since back EMF is negligible, this is negligible at low speed. So we can consider applied DC, high DC voltage L di by dt. And that's the reason in low speed what we can see is that since at low speed, low inductance value, if you turn on the phase here, if you give high voltage DC, VDC applied here, okay, what happens is that the rise in the current di by dt will be very, very high at low speed. At low speed, when you switch on at low inductance value, so whenever you go in this region, you may get into very high di by dt that will go to very high currents at low speed. Okay. Now at low speed, the best way control strategy is that we will, though it is going to very high current, we will try to limit the current. So this limiting current is at low speed. Okay, so when the motor is in low speed, it is preferred that because of high DC voltage, high voltage DC, it will go to very high current because of low back EMF. So we have to limit that current through the hysteresis. That's the reason at low speed you have hysteresis control. So since this current will rise to very high value, we will limit the current to I reference. Now as I told you, I reference T on, T off will help us to understand and get the torque. Now when it is T rated, so we have to maintain that I rated reference. So we will put the hysteresis control, and one of the control strategies is hysteresis control, we put the band control. So we will put that controller within this period of positive torque. And during demagnetizing, we will see in converter that when you turn off, the demagnetizing region itself is giving the negative voltage to it. So we don't have controllability here. So we have only controllability on these three parameters: I reference, T on, and T off. Now, as speed increases, what happens is that this back EMF, as speed increases, this back EMF is going to come into picture. Now, as speed increases, back EMF is going to increase. When back EMF increases, the actual equation becomes like VDC equal to, instead of now it becomes L di by dt plus back EMF EB. Now, if you see that this back EMF will come this side, that means VDC minus back EMF is L di by dt. Okay. Now this you can see it has reduced the voltage. Now what happens? As speed increases, since the voltage is reduced, the reduced, that is P minus ADC. Now the say you can see that when this inductance comes down, so you have seen that because V minus EV by L, you can see this voltage is reduced. That means your di by dt will reduce. Okay. Now interestingly, as you go to higher speed region, okay, it will fall within the limit one. Because as speed is increasing, your current is actually kept at maximum limit. Okay, and because of back EMF effect, the current will fall. You can see it here. Now in high speed region, the only means that you can increase this area. Now remember always one thing, this entire area of I reference T on and T off, I reference will contribute to the torque. More this area, higher the area, higher the torque value. Fine. Now what happens is that as speed increases, since this area is falling down, you won't get the required torque levels. What you have to do is that at that moment, at higher speed, it is better to push this T on control. So at higher speed, you can control this T on and make it that at earlier only you can get into more current, and more current will result into a more torque. So more area will result into more torque. Now in a nutshell, at low speed, it is better to have switching between hysteresis control because current will go to high value. At high speed, back EMF itself is going to limit. That's the reason we can have control through T on, fixing T on. There are a couple of control strategies. The simplest control strategy is that in low speed, work with three parameters: I reference, T on, and T off. And in higher speed region, by varying I reference, and higher speed region we can control by T on to get more torque. So this is the simplest approach to understand minimum control strategy of any reluctance motor. And we will try to see some cases of that on some simulations and understand the principle. So I hope that I'm not connected one-to-one in conversation due to some technical issue. But I wish that by now you have understood that what are the essential parameters to control the reluctance motor drive. And this is the overall control strategy. We can see here three parameters are essential for us. We need to get I reference, okay, and T on and T off. When it's low speed it will work with I reference, T on and T off. And when it's high speed, it will work with T on and T off. Now we can see it here as a simplest outer loop control, that is speed control. We will see the speed of the actual speed of the motor and reference speed. The error is processed through PID controller, and we know very well in basic drives is that the outer loop will decide the inner loop, that is torque reference, required torque. Now this torque reference has to be converted into current reference, and we know very well this is a quadratic relationship. As we know very well, torque is proportional to square of the current, and if you want current, it's nothing but root of torque. So if you have torque reference value, if you put the root simple, then you get the current reference. And this reference and T on and T off will help to control. That's all. Okay. And at higher speed, the torque reference, the required torque, and at higher speed we are mapping between what is the torque required. As I told you, T on should be controlled with reference to the torque. So we will map with the reference to torque and omega. So the lookup table for torque and omega can be made for T-on angles, keeping T-on either fixed or a variable also. So that's the reason in blows at high speed what happens is that this will switch on to, instead of hysteresis control, it will go into only angle control. Okay. So when you go into angle control, we are only controlling through T-on and T-off in higher speed. So we can see this is the top reference coming and I am taking the actual speed, and for this what is the T-on calculated value, estimated value, and this estimation comes from the analysis that we do on the motor type. So with this T-on and T-off we can control in higher speed region. And basically other challenge in reluctance motor is that this is very essential part to learn that to control the motor, if I want to control T-on and T-off, that means I need the position information. So position information is very essential part in this case. That's the reason for a drive we need to have position information. That position information will help us to when to turn on, when to put the controller. Right? So this is a need for that one. Though a couple of control strategies have been already been built. Okay, the basic controller is a requires position sensor. Nowadays we have sensorless controls also. Okay, now a basic system of a reluctance motor will have this position information and when to turn on, with what should be the current reference. This is what we can learn in the control of reluctance motor drive. Now when it comes to topology, we know whether to switch phase topology. What happens is that I just want to brief with this, though it might be covered there. So when S1 and S2 are on, this is classical topology, the VDC is applied to the coil. Okay? And there is a mode that when S1 is off, only when S2 is on. So that means it will free, the energy stored in this one will free will through this. Okay? This is when positive VDC 0, positive VDC 0 applied. Okay? Now this is called soft switching. When what is meant by hard switching is that, so when both are on and both are off. Okay, when both are on, both are off, it is positive VDC, minus VDC, positive VDC, minus VDC, positive VDC, minus VDC. So this is called hard swapping, this is called soft swapping. Okay. Now the other part is that once the switching pattern is over, after switching is over in that one, when both the switches are off, when both the switches are off, this is off, this is off. Now what happens, the energy stored in the inductor will freewheel through the diodes. Okay? So this concept of freewheeling is called demagnetizing. Right? So this component is actually controlled by the system itself, by the inductor itself. We don't have during this period any control over S1 and S2. So we can see it here. This is what we can see. This is what we are turning on and turning off. This is our control part, T on and T off, when to on, when to off. Now, when after off, right? After off, the demagnetism, the minus VDC is applied by the system, okay, through D1 and D2. Okay, so this is demagnetizing component. Now, this actually helps us in saving energy also. So this is a regenerative component. So what is the thing is that we can see it here is that, so during regeneration, this energy is given back to the source. So demagnetic component saves little energy back to the source, and from source we are getting energy, and this capacity will help us to energy buffer between the source as well as the coils. And basically the other topology is alternate topology, single switch per phase, we are exciting single and demagnetizing done by other phase, other switching. So that's about reorder. So most widely used is classical single two switch per phase topology. Okay, I hope that you understand now. Now only thing that if power circuit is same, the significance comes with the switching, when to switch on, when to switch off. So when I am able to switch on and switch off, if I know the position and switch on and switch off, that will be sufficient for me to control the server. Okay. Applications of that one, I will try to skip off that one. So that's about the basic control of reluctance motor. And for essential part of that one, as I told you, we should have the knowledge of flux linkage characteristics. That's what we will see again, how to do that thing. So I hope that the basic of the control aspects of reluctance motor is been understood clearly. And we'll see now, we'll try to model the system and then we'll look to that. Any questions till this part? The audience, on their audience, you can put it in chat also. Somebody can put.
How should you say the turn on and turn off angles, numbers?
If no questions, we can go further. So I hope that there's no questions. I'll try to just go to.
Any more questions?
Now, let's try to learn about modeling of reluctance motor.
Sir,
The first point that we'll try to learn is significance of the flux linkage characteristics and how to get these characteristics, how do we determine the characteristics, in what ways we can determine the characteristics, and then how do we compute static torque characteristics out of it and MATLAB simulate model and try to see some result that has been already there. So this was okay.
We'll see that.
Vijay sir.
The first thing very important for us to learn that we begin at this point is that we should.
Idealization of flux linkage characteristics will give us model with the performance with it cannot predict the model with the accuracy. Okay. So this is the essential part to have flux linkage, and linearization or idealization of that one is cannot predict the performance of that one with sufficient accuracy. So the model, there are a couple of models authors have worked with the linear models and everything, but they won't be that much accurate or relevant kind of system. Whereas when we consider non-linearity of the flux linkage, it is very good modeling, it will have more accurate, but complexity in modeling is that because of the non-linear flux linkage characteristics. And it is very difficult to get it a mathematical relationship between them. So, couple of the ways in motor drives to get the flux linkage characteristics of any motors are, one of the methods is using finite element method tools, okay, like any tools like ANSYS or JMAC or electromagnetic tools. So, EM tools will help us to get the flux linkage. And the real challenge of this method is that finding the characteristic is that you should know all the dimensions of the motor. All the dimensions, materials, properties, all that thing you have to learn. But these are very good at the stage of before designing a motor. So they will help to design a new motor, new topology. So while designing, this will help you to optimize to get into that one and finally come up with the design. When you have already a motor that has been already procured, already been there, the way to get the flux linkage characteristics is that doing experimental approach. Fine. This holds good when you have a motor. Okay. So in either the way, if you have a motor, all the dimensions, materials or anything, you can get the flux linkage characteristic through the tools. Okay. And if you have a motor and if you don't use any electromagnetic tools, the other approach that you can do is that using experimental approach, that is direct measurement approach. And 1 minute, just I put a chart.
Guys, 15 minutes break.
I think so. Mr. Kumar will inform you about the break. After that, I think so we will start back from 11. Yeah, no.
Okay, sir.
I'm audible.
Yes, sir, it is audible. Sir, my voice is getting.
Your voice is coming to me.
Okay, sir. So, first question. Sir, right, sir.
1 minute, 1 minute.
How to numerically decide the angles? What
Oh,
is the
okay.
angle?
1 minute, 1 minute.
So, how to decide the rotation angle?
Hey. 1 minute.
Tan and tan off angle. Turn on and off.
I'm audible now?
Yes, sir.
Yeah, fine. So, turn on and turn off, identifying that one, we will come to that one because that's part of that one. We will be addressing that issue. So, I think it will follow. No issues. That point we will discuss. It will be followed. Is that fine? So turn on and turn off angle depends on the torque ripple requirement and everything, where the torque has to be based on the torque ripple, where it is high, where it is low. Selection will be based on that principle. That also we'll try to address it and see. Okay. I'll show you an example of it. Fine?
Yes, sir. One more question. What motor you are using? Rating of the motor.
Yeah, there are a couple of models that we have worked. I worked with initially when I was doing my master's, I worked with 4 kilowatt motor, that is Alton drive. And in NIT Warangal, I have worked on 2.2 kilowatt motor, that is there. And then now in my lab, I have around 500 watt SRM reluctance motor.
What is the rated speed? What is the rated speed?
Rated speed. The rated speed of 2.2 kilowatt motor is 1500 RPM when I was working in NIT Warangal. Then the 4 kilowatt motor was rated with 2.2 kilowatt motor was rated with 3000 RPM. Then 4 kilowatt motor was rated with 1500 RPM. I think so. This small power fired motor, which is typically high speed motor that currently we are working with 5000 RPM.
Okay, sir.
So can you go more than that? Will you operate the motor speed or range of speed? Range of speed. What is the range of speed? Minimum range.
Sir, what is the minimum range and maximum range we can operate?
Minimum range and maximum range of any, for example, if it's a 4 kilowatt motor or we had a 2.2 kilowatt motor, it was rated with 1500 RPM. And typically we can go at till the 6 times of the rated RPM. That is 1500 into 6. Typically that's value we can go with reluctance motors. 5 to 6 times of the rated speed we can go to the motor to work.
So just 1 second, sir.
One more question.
Yes, actually, Vijay Bhaskar, myself, faculty from associate professor from NIT Rourkela, and so nice to meet you. And so your explanation is very nice. Actually, my question is that you are using the PID controller, right? So in general, we will use that PI controller for maybe like for induction motor, for any of the motor applications. So okay, is
it was basically drives. Most of the drives are susceptible. Control is done by PI.
okay.
D is little bit sensitive to the noise.
Nice, yes.
Only when there is no transients, when there is no transient applications, we prefer to choose D also
Okay.
to minimize the overshoot.
So as you are using that like SRM motor, so due to some noise, you are included that, I think so, that D controller, right? Differentiator.
We are not used the DS.
Okay.
We are Moses PI only.
Okay.
To one extent, if at all is needed to minimize overshoot.
Okay.
To minimize the overshoot, we use D.
And then sensors for sensing of for the all sensors only. Okay. 3 sensors you are using for that, right?
For SRM 8x6 motor is
Okay,
4-phase motor. We have used the 4 sensors within that mounted on.
Okay. For each phase you are using for 1, I think so. That way you have been used.
No, even actually that depends on sensor mechanism control strategy.
Okay.
Preferred is 4 sensors. If you have more number of pulse widths, you get more intermediate accurate positions you get.
Okay.
If you have more intermediate accurate positions, that will help you to accurately get the speed value.
Okay.
And if you have even 2 sensors also, it's possible to have 4 combinations. On, off. So 2 into 2, typically 4 will get.
Okay.
But if you have more 16 samples between 60 degrees, you will get more interim accurate positions to identify actual happening speed.
Okay.
Or else, what happens is that intermediate stage, you have to just assume and you have to just integrate and you have to get the position of the speed. So that's little less accurate, but it's possible still.
Okay.
So interestingly, even if you have one Hall sensor also, you can work. I have built that algorithm.
Okay.
It is just one Hall sensor is enough. One information is enough for me to identify entire position.
Okay.
Every rise I am identified. So accurately, how accurately you get in between is up to you.
Okay.
So logic is a logic driven. 4 sensors if you use 16 logics will get 0, 1, 0, 1, 1, 0, 0, 16 combinations. 16 combinations will give you 60 degrees. So you have more intermediate accurate position information.
Okay.
And type of sensors, if you use encoder, we know very well. Yes. But encoder will give 1024 pulses within the entire span. So that is more accurate.
Okay, thank you.
Are used minimum.
Okay.
But algorithms can be built, sir.
Okay, fine. Thank you, sir. You can proceed.
Yeah.
Hello. Good morning, sir. One more question. Hello. Hello.
Vijay sir, one more question.
Yeah.
Sir, I am impression sir, part-time scholar. So I am me also working on same SRM there, sir. So you suggested we need to turn on switch before the actual position. So if rotor
Little closer can you come out? Here. Yeah, little more.
sir.
Hello?
Hello, sir. Am I audible, sir?
Yeah.
Sir, to overcome one issue, so we need to turn on switch before the actual position. Actually, you suggested, sir. Yes, sir. Yes, sir. Suppose if rotor polar and stator polar are same, so no gap between the increasing induction profile and decreasing inductance profile, sir. If we start before, so that is maybe generating mode. So it will produce this negative torque. So maybe average torque will be decreases. Is it correct, sir? Yes. So is it suggestible for that? In that case, is it suggestible, sir?
I'm trying to put my PPT and I share. Sir, Krupakar, we are not able to share the screen. Present. Is my screen visible, sir? Yeah, now I think it's back. Sir, you're talking about
Inductance profile, sir.
this now?
No, yes, sir. This one. But go to first before slide, sir. So actually, so increasing inductance and decreasing inductance both are start at one position. If we start, if we give the switching pulse before the actual position, so maybe that will enter into the generating mode. Is it true, sir?
Yeah, slightly generating mode.
Generating mode means negative. It will produce negative torque. So average torque maybe decreases. It will decreases maybe.
This region, couple of degrees from this side or couple of degrees from this side, okay, will help us. Means is almost similar lengths. Like you don't have much change happening in that way. So when you go to higher ratings and everything, if you switch on in this region, okay, it's still not having that much torque, but this additional torque is going to help us to produce more torque positively. Though we have to put on exactly switching, look to proper way of what we call as how much negative torque is going to come. This happens, but you have to choose in such a way that angle that you have to help out that you have to produce positive torque and more torque production has to be done. Typically, you can go till -5 degrees.
If beta R is greater than beta S, so is it suggestible? So it is suggestible. But if beta R and beta S both are arcs are equal, stator polar arc and rotor polar arc are equal, so no gaps are actually both. Yes, sir. So in that case, it will produce negative torque.
Yeah. In that case, it will produce negative torque, but by the time what happens is we might have already attained, in that case, we might have attained it is only essential when we go beyond the rated. So there is something called as flat top region of the curve. So where back EMF is actually equal to VDC. So nearly equal to VDC. So during this point we have flat top of the curve of current. Okay. Now beyond this we are going, we need to have more excitation angle to advance angle for control strategy. In your case, I think so when rotor poles, stator poles are same, I think you don't get much. But we have to see that till what point you will get this flat top curve and what point you will get the rated top. So that's only we have to switch on, we have to see, sir. See to that angle to where it reaches. Only it happens is that when we have rotor pole and stator pole in the same weight, then you don't have much scope to control strategy.
Yes, sir.
Or you have to push T off also.
Yes, sir. Yes.
So T off can also be adjusted along with that such that you have more area. So, but only thing that contributes is as T off is pushing towards this region, you have more ripples. If ripples are compromised, I think so down the line you can push it more. When you don't have scope here, you can push it into right.
Okay, sir. Thank you.
And are you asking about this also generating more? Why I am putting it here? Is that question also? No. Right. So this also actually what happens is that no generator will work without excitation. So we have to get excitation as a generator also. Generator needs a magnetic excitation. So this small region, before you move to generating mode, it will look opposite curve. So this is the excitation, and you have more current in generating. Through this waveform, there you will understand that small excitation is actually required because it cannot have self-generation. That's also techniques are there. If you have magnets and everything that can help you in generation. But without magnet, you have to provide a small magnetic path for excitation to get into generating mode. That's the reason a small region of excitation is required for this generating. But I think a couple of people may have question on that.
Yes, sir. Okay, sir. Thank you, sir. Thank you, sir.
Fine?
Yes, sir.
Sir, one more question. Sir, regenerative mode of operation. Can you explain?
Regenerative?
Mode of operation.
Regenerative mode of operation this way that wherever you are give the excitation for a small duration and that get more current. Maybe I showed the generator waveform. That I think so we will get an idea. Okay, here we can see that will be useful. We can see that this is the motoring mode. Now when I am switching in the positive region, I am getting the positive current, and we can get the positive torque. And this is what we can see. This is magnetizing component and this is a demagnetizing component. Right? Now we get in positive torque. The next part we can see is a part of generation. This is helping in generation, this is helping in motor. Okay. Now in opposite, what happens is that if this curve remains opposite, that means you have excitation this side, generating mode this side. So for a generator, you can see I am switching in this direction. So I am switching here, and when I am switching in this direction, this part is your excitation required for the coil. Okay. Now always remember that one challenge that we will get is that in a generating mode, any generator, the question that comes is that how do I give this excitation? So because definitely there has to be some magnetic field. Because if there is no magnet that it can be rotated, or there is no magnet, obviously that cannot produce the generation. Generation cannot be happen without the excitation. Either it can be excited through coils. Okay. The other means people use is that magnets for a generator. In case of magnets, there is no challenge, no issue, because magnets will be moving, that will create. Cut the coil will induce EMF that will produce energy. So that will act like a generator. But in case of generators without the magnets, okay, the only means that we have to give is that we have to create that electromagnet at the phase. Excitation requirement is there. So what we are doing in this region is that we are exciting the phase and we are creating that magnetic. Within that magnetic field, if rotor is moving with mechanical energy within that one, that will be generated. So this region is actually generating region. So this will give you more. You can see the area is more, the excitation is less. So excitation is less and the area of this one is more, indicates that you are producing more energy than excitation. Right. Now, a couple of my part of thesis work when I was working with a generator for wind energy conversion system is that how do I get this excitation? So this piece is also called as self-excitation method. Okay, and there's something also called as initial excitation. So at the start, how do you get initial excitation? Either through capacitor which is already stored or through some magnetic energy. There are different methods of excitation of initial excitation. Now, part of my work was that if I use solar energy, nearby solar energy, that also helped me for the initial excitation. That will keep into generating motor. So, all of other works are there. So I think so this will help you to understand generating mode. And we need excitation, and how this comes is a question. Okay, and the control strategy remains same. Exciting in most of the region it should be in the negative slope region. So this is 0, 60 degree. So 0 to 30 degrees we need to work on motoring. 30 to 60 we have to work for generating. And this configuration changes based on type of the motor. Is this question clear?
Okay, sir. Thank you, sir.
Okay, let's go to the main one time. Stop with try to push up. Good. So now we have reached that, and this is a three-dimensional view. Now, flux is a function of current and position. That's what we have seen. It's a function of flux is a function of current and different positions. Okay. Now in three-dimensional view, it will look like this characteristics. Now the static torque characteristics also over the positive and negative character. Now understand that after 30 degrees, from 30 to 60 degrees, it is actually negative torque of the same. It's the same characteristics but in a negative way. So we can rebuild if you have 0 to 30 degrees developed, that is sufficient to build with the negative values from 30 to 60 degrees. So that is the negative torque region. So overall, basic block diagram of any simulation model of reluctance motor requires the flux linkage characteristic, that is current characteristic. Current is actually a function of flux and position theta. So this information, and then torque is function of current and theta. Okay. So we need to build these two information more accurately into the model. So after that, if you know the flux, this is the flux, this is nothing but a voltage equation. You can see it, voltage equation. So flux is nothing but integration of V minus flux is integration of V minus I into R. So V minus IR, I is coming, V minus IR is integration, you are getting flux. Now flux is an input and then theta is another input, you are getting current. So this characteristics is essential. Now once you get the current, you know position and current. For the position and current, you will get the torque. And 0 to 30 degrees if you do, you will get positive torque. And 30 to 60 degree, you will get negative torque. And rest all is this is the mechanical equation. This is electrical voltage equation. Any motors can be classified into the models can be classified into voltage and torque equation or mechanical equation. Now you can look to that one. This is the current characteristics, and it will be again from 0 to 60 degree. We have three-dimensional view. So this is also torque characteristics, function of current and theta. Now if these two data are available or we build, so this data can be built using even FEM models, okay, modeling technique, or as I told you, experimental approach. In both way we can build this model. And this is essential for us to have accurate accurate control of the motor. So once we build, we can clearly see that this V minus I are putting integrator, and we are building that lookup table here, and this is lookup table approach. And there are mathematical approaches where we can also put this flux as a relation of current and theta in terms of mathematical equations also we can. So during my master's, I think so my paper, one of the paper on switch related generator has that equation based modeling. So where flux can be equation and current can be computed with the current estimate can be done. So mathematically also we can build. Even torque equation can also be mathematically represented. So approximations have already been built. There are so many models built in. Now one of the approach, very fundamental approach is that if you have the data, things which is put up in a lookup table, then use that. So this is a resultant torque. This is a mechanical equation that we can build. So as I told you, this is the motoring mode. So this requires position information, very very important. Unlike other motors, even in permanent magnet based motors, we have position sensor requirement on it. So here also we require position. Based on the position, we need to switch on and switch off the voltage. So giving the voltage to this one. This is a excitation, and based on which position I am going to give the excitation. This is essential part in reluctance motor. Now we have sensorless controls also very well established for reluctance motors. So motoring mode, positive torque, negative torque, we have generating mode with a positive omega. The other point that we have to learn with a little bit advanced control strategy, or I'm just letting out my thesis work, the part of the work that we had worked in NIT Warangal is that one of the learning curve is that the excitation, when we see this excitation of the coil, sorry. You can see the excitation DC voltage. When the DC voltage is very high, and we are switching on, and because I already told you, when DC voltage is high, current will go high, we need to put on switch on and switch off, and that's what we have seen, that hysteresis control has to be limiting the current, since the DC voltage was full high. So that's the reason we require hysteresis control in low speed region. So when this fixed DC voltage which is high, so which will current will rise in a very high value, we need to limit the current using limiter, okay? And because we know it's back EMF will be low in low speed, we need to have fixed DC voltage which is high. It will produce very high, and that's the reason we need HCM control, hysteresis control mode. And this need current sensors, because we have to sense the current, then we have to limit the current. So this needs sensors and it needs current limiters. So current limiters also required, and also conditioning circuits are required, because sometimes what happens, because of hysteresis, the bandwidth, if you close less this bandwidth, you will have higher frequency. So higher frequency may not be possible to switch on the IGBTs required in the circuit and everything. So we have to put limiters for that one, less than 10 kilohertz switching mechanism, we have to limit that one. And those are also required when you put on to high voltage DC hysteresis control. The other way approach is that interesting approach that we can identify from Pandas's thesis. Pandasar has done in IISc Bangalore. They have done a thesis on reluctance motor. Based on their work only, I started to work and develop that one. So one of the work suggested that interesting work is that, what if this voltage is decreased? What if the voltage is limited at the initial only? If I minimize this voltage, what will happen? So we know very well VDC is equal to VDC minus back EMF equal to L diabetic. This is what equation we are seeing. At low speed, this will be very low or typically zero, right? And at low speed, because of that, this is very high value. That's the reason we are getting high diabetic. Okay. The interesting point that was thought is that what at low speed if I also reduce the voltage and C. So if I may reduce this voltage in low speed if I reduce the voltage, what happens is that my equation becomes VDC, which is low, okay, becomes LD di by dt also reduces. That means instead of going into very high, the slope of that one will fall very low. Again, it might be a chance that it may come into angle control only, fall in that limit. So in that way, what happens using variable DC control strategies, it will make you to enter into single pulse mode by varying VDC with reference to the speed. So if you vary VDC with reference to speed parallelly or linearly to one extent, we can get that it will always work in single pulse mode. So that was the idea of Parnasar's thesis, where variable DC, but advantage of that one, what will be that one? No, you need not check for currents. So current sensors or their sensors, you don't require. So it will eliminate these sensors. And after that, also since it's not giving hysteresis control, even limiters are not required. Okay, because they are working, this is at higher frequency, whereas single pulse mode is low frequency. So obviously, even the condition circuits required for that one, all that thing will be reduced in case of if you create a variable DC instead of fixed DC. Okay, that's the key role or the key aspect to understand the elimination of hysteresis control. Now that's called variable DC control strategy. Now with variable DC control strategy, if you vary with reference to speed, so with reference to, you can say this is the fixed DC. If you vary linearly with reference to speed, okay, it can eliminate need of sensors, limiters and condition circuits. So that's a interesting point that we can learn. So variable or reduced voltage during commutation will also help us in another important point. So this is what we have to stress here. Now, hysteresis control has another drawback is that if you have a loop of that one, there is a possibility of having plus VDC to minus VDC, plus VDC to minus VDC, the rise or the fall of the current, the di by dt in this case, will be very high. And high di by dt will result into more vibrations, noise, all that thing will come into picture. So higher this DC link. Now to minimize the noise, interestingly, this in variable DC control strategy, if you have a fixed DC control strategy with angle control mode, even you have positive VDC to negative VDC. So we have this 2 VDC control. Whereas if you vary this voltage as proportional to the speed, at low speed, this VDC will be low. What happens is that because it's a low one, okay, this the lower version of plus VDC to minus VDC, lower voltage, will have low di by dt, and this will result into low vibration, noise, all that thing. And vibration typically happens during this period of transient from first plus VDC to minus VDC, and that impact we can see that if you reduce the voltage, in simple way, nutshell, if I put it, if you have variable voltage and you are during commutation, if you have variable voltage, obviously it will help us to reduce the noise and it will help us to eliminate the sensors. So that was the principle of variable DC control strategy. Now, the challenge of this one variable DC control strategy, fixed higher DC voltage, is that irrespective of that one, there is still vibration. So there is still vibration in this control strategy. We cannot omit the vibration because you have to give commutation plus VDC minus. What if I introduce positive, negative or positive, negative during that time? There might be a possibility that I can have a zero state also. So this zero state is not possible in this case. So if you give zero state plus VDC, 0 and minus VDC, this will minimize even noise also. Okay. Now the idea that we thought that we started to work with, started to explore is that to bring up a PWM control strategy by which we are eliminating stress because there is no stresses PWM control strategy. We are working with the duty cycle. And there is a possibility of having zero state also, which is not possible in single pulse mode. By that what happens is that we have lower noise and lower vibrations and everything, and also it will also we can see that since it's working on PWM technique, the current limiting or current the current limiter required, or we are just avoiding stresses. And stresses is because variable DC. Right? So at low speed, what I'll do, I'll start with variable DC and the duty cycle. Sorry, duty cycle. So if I change the duty cycle, I can change the rise in the of everything, and but the variable DC will help us to eliminate stresses, and noise can be minimized with the zero potential that can happen. So this was the idea that we started to investigate, and we have put this into water pumping application, and we started to do some small experimentation of prototyping and everything. So these are the three control strategies. We can see the simulated models of that one. Here you can see stresses control where we kept the band of 0.5 amp, and we started to look with the control strategy. You can see that we are getting stresses control, and 4 phases will come into picture. So we have other 3 phases contributing. We'll try to see the waveform also for understanding. And this is single pulse control strategy. So since here VDC is high, we can see that there is no possibility of zero potential here. Whereas there is a potential of having zero positive and variable DC. We'll create variable DC which will eliminate stresses control also. So the motor was rated with 240 volt, if I remember, 240 volt DC. So we need not, when it's not higher voltage, okay, when we need to have high stresses control, and because we can lower the voltage, we can eliminate that one also. Now all 3 parameters, 3 control strategies can be investigated. This is a practical waveform that we got. This was the stress control, and this is the angle control, single pulse mode, and this was PWM control strategy. For the same parameters, we started to test. This was simulated, this was tested. Now, the investigation of this one, stresses control, single pulse control, PWM control, was one of the parameters. I just want to briefly talk those part of the thesis for the water pumping application. But initial study we made with between these 3 control strategies to know a couple of points. So that will help us to understand what exactly we are trying to do. So this was a practical setup that we had in NIT Warangal. This was a reluctance motor. Now we were trying for pump load. So for pump load, we know very well it's a quadratic load. This is also a very important point that we will discuss again. So torque is proportional to square of the speed. Okay. So this is what you can see. The power for the loading for power is cubic of speed. So for this we try to validate for this power curve and see that at different speed what would be that one. So we can see peak current. This is stress control. What we can see, the diamond shape is nothing but stress control. This is stress control. We can see peak phase current, okay, is low, okay, Typically we can see it around 2 amps to that one to maximum rated is around peak current here around 4 amps for the small load which started to test. Okay. Now SPM single pulse mode, we can see single pulse mode we have having higher peak current. Okay. So because we have given full VDC and fixed VDC, these three are in fixed VDC, these two are in variable DC. So full VDC in single pulse mode will give you very high current. So peak current will be high. Okay? And as a result we can see it clearly that peak current is very high. The next is even PWM technique with higher voltage DC, with a fixed DC voltage. If you have fixed DC voltage, you can see it is PWM technique is helping us in having lower peak current compared to even hysteresis control also. And compared to single pulse mode, the variable DC peak current is very low. Okay, fixed DC. Where is the black dot? Yeah, this is black dot. Right? So next, what we have carried out is variable DC SPM technique. So variable DC SPM technique single pulse mode, where we can see it, the peak current is actually lower in the lower case because they have reduced the voltage in lower speed. Okay. So because of that, we can see that it has lower impedance and finally it reaches to its own condition, both remain same. Right? So that's the reason variable DC will help us to minimize even the peak currents in lower a single pulse mode. And finally, when we apply this variable DC along with the PWM control strategy, we can see it is helping us in low peak phase current. So current is low. So peak current gets low in this control strategy. And other performance parameters that we can investigate and see is that this is practically often one. Try to investigate it. That one is that even torque ripple is also very essential part. So we can say that ripple is in case of because the hysteresis work on ripple based hysteresis control on current control is very good in torque ripple minimizing, but it requires current sensors. SPM with the fixed DC also at higher DC will help us to minimize the will have more torque ripple, whereas when we see the variable DC PWM strategy is having lower torque ripple throughout the region. So this will help in terms of minimizing torque ripple, which further help us in minimizing the noise and everything. So this was measured noise through the noise meter. We tested that one, and we can see that typically around more than 5 dB of reduction in noise, especially in low speed region. And even in high speed region, we can see from the control strategies from the SPM, as I told you, since it's positive VDC, negative VDC is going to come. Definitely this is causing more higher noise compared to other strategies. Now PWM also has a positive, negative and zero possibility. That's the reason you can have lower noise with the zero possibilities. Whereas variable DC and as I told you, because reducing the voltage will help us in reducing noise also. We can see it at lower speed, but as it goes to high speed, it is reaching along with the fixed DC. Okay. And noise in terms of variable DC PWM technique, okay, it is actually completely reducing the noise, and it's contributing at least 5 dB reduction in noise, 5 dB to 7 dB reduction. This is actually a very good level of reduction in techniques. And also efficiency also we tested to find the efficiency, and we can see that efficiency is also very good in variable DC PWM control strategy. And what would be the advantage of that one is that we are eliminating sensors from HCM control, and we are also eliminating the noise of this one. Noise also eliminated for that, and these advantages are reflecting with variable DC PWM control strategy. Because of variable DC, we are eliminating the sensors, the current sensors. Okay, and because of PWM control strategy, we are minimizing the noise. So with that, what we can say is that summary of variable DC PWM technique is that it will reduce the peak current also, and lesser torque ripple, noise, and better efficiency. Also eliminates the current sensors and current conditioning circuits. This we have seen in a practical way. Is the point clear till this point? Anyone have any question on this? Have any question to ask, or we shall be move on?
Okay, I'll ask.
Okay. Yeah.
Actually, you have used that current controller, right? Like.
Yes.
So,
Yes.
my question is that, like, as you are maybe operating for a different speeds or maybe a different operating conditions, so how you are fixing that reference current? That's what my question.
Yeah,
As
that will
dealing with the torque controller also.
yeah, fine. Fixing current, the maximum current has to be fixed with the maximum rated current, rated torque of the valve. So in your controller, if you see the controller, the torque reference will give you the current reference. The load and fundamental point in any motor drive system is that always this is very fundamental point to learn or to concentrate is that, okay, when you change VDC, when you vary the VDC, most of the motors in general, when you vary the VDC, you can change the speed of the motor. Okay? So when you vary the voltage, we can change the speed of the motor. If it's a DC motor, simple. DC voltage, if you vary, we can vary the speed of the motor. If it's AC motor, we are changing AC voltage and frequency both to get variable speed. So this is for DC motors, this is for AC motors. This is basic principle. But the other part is very essential to learn is that it is not that if I change the current, I get the change in the load. This is totally the wrong principle. It is the load, if you put the load, then you will draw the current. This is very important to understand. So it is the load that decides the thing. Or if I put in a single statement is that it is the load that draws power. Fine. So when there is a shaft, and if the shaft, if you put the load torque onto it, then only it will draw the current. Now here also you can see it here. The torque reference is deciding the current requirement. If there is no torque requirement, okay, if there is no torque requirement, obviously your reference will fall. So that means lower the load torque, lower the current reference. Okay. So we already have learned that one. T on, T off, and I reference. I reference decides the torque value. Okay. Now what is the load requirement? Then only you can put it to T reference. Now if you fix it to maximum value, maximum torque, as speed increases, what happens is this area is going to squeeze. When area is going to squeeze, the current will not rise to that one, it will fall within that one as speed increases, because this is going to come down, area is going to come down. So by that what happens, torque also is going to fall. Right. So current control, if you want to do based on the current, based on the torque, as per the torque you have to map this I reference value.
So if you want to maybe going for above rated speed, again current is again further decrease.
Increase. Above higher speed, at higher speed.
Yes.
At lower speed, for typical EV application, what happens is that at lower speed, we'll see this. At lower speed, you need to have high torque, right? At low speed, you need to have high torque. This is the requirement. Okay. At that point, what you're going to do? You have to increase the current reference.
Yes,
when its speed is low.
for above rated speed, like
above rated angle control.
So that maybe current should be decreased, right? So that's
decrease.
what okay, fine.
So Yeah. Another beautiful point about reluctance motor is that, which we can see that it is relevant to the EV application, is that this is what we can see. We will try to see the simulation of that one also. So we'll look to that part in now. Okay, next session. Any other thing? So we'll look to a little bit into EV because I wanted to bring this point of reluctance motor by relevance for the EV application. So any vehicle characteristic, I quickly go through that one in a simple way. That's very essential to learn. Any vehicle characteristics require a constant power region. That means that the torque should fall as speed increases. So this is hyperbolic characteristic. This is actually ideal requirement of the vehicle. Now practical requirement of any vehicle is that at low speed, this is a rated speed. Okay. At rated speed, you need to have high torque, T max. Okay. And above that, it should be in constant power region where torque is falling. Okay. Constant torque and then falling of the torque, constant power region. So in IC engine, because engine characteristics is there, it cannot match. That's the reason we need gear requirement. I am not going in detail of that one. So whereas in electric motors, this is the beauty of the electric motor is that vehicle characteristics, which is practical characteristics, is directly mapped with electric EV. So EV's characteristics are already having this constant torque till the maximum speed. After the rated speed, till the maximum speed, this is the max vehicle speed. Okay, this region should be more. Okay, expected should be more. This should be low. That means as much as for low speed, it should have higher torque available. Now, the SRM control strategy is that it is very suitable for this kind of applications. Okay, I'll just try to show that the simulation. Switch reluctance machine application already one of the application is there. So motor particular characteristics are required. If at all you have particular characteristics within your circle or available data, you can use that one to model that one. Whereas a model examples we can see to learn the model example, or that one we will see this example. So what we can see is that, I'll try to put it before it opens up kind of thing, I'll try to put it here for our understanding. What we have learned is that T on, T off and hysteresis. I reference, T on, T off. This is under low speed, right? So we can have higher torque. If you maintain this I reference, at low speed, it will have T max. So at lower speed, once it is crossing that rated speed or rated speed condition, okay, at rated speed, what we can see is that we require at rated speed, over the rated speed altogether, we have only angle control, right? So where current is falling less than this manually, the area is less. So say for same T on and T off, I am not varying T on and T off. If I fix T on and T off and I give current reference, at initial current it will have higher torque will come. At later stage, if I don't vary the T on T off, my torque, because area is less, area is falling down, that means my torque is going to fall. Now interestingly, if I fix T on and T off and if I give current reference and just turn on the motor and run the motor, you can see that it will be having maximum torque. After maximum torque, the torque starts to fall by itself because area is less. And by virtue, this characteristics is very easy in reluctant motor. And this is what vehicle requires. Unlike in ICs, unlike the other motors, it is easy to get into that one. Now we know T on T off I reference. That is sufficient for us to look to that. A minimum example kind of thing. Let's take 8x6. We know 8x6. I'll try to breathe this one. I think so. If at all you are also having MATLAB system, you can open this switch reluctant machine example, and then till now whatever we have learned, we'll try to adapt into this and see what are the things that are available. Okay. Now see, only parameter, control parameter is that I'll just brief on this model. So this is a classical topology. If you open and see the classical topology, right? So it's a two switch per phase topology, and then if you open this motor and I put it right click and if I see in the mask, look under the mask, okay, I'm going to look under the mask, and if I open the model, you can see it here. The model is completely built on the characteristics. Okay, fine. So you can see the first equation that I told you is V minus IR. Okay, integration is in a discrete mode. Integration of that one will give you the flux. Flux and the position. This table will help us to identify the current. Okay, this is a built-in model. Even you can put your data if you have your experimental data. You can put that experimental data and you can get that one. And the other characteristic essentially is torque characteristics. You can see torque, current and theta are the input for that one. And then this is the load torque equation, which is simple mechanical equation. Torque developed to the load torque. So T minus TL by J will give you the load torque equation. Integration of it's a d omega by dt. Integration of that one will give omega. Okay, so this is a very simplest way to, if you have your practical data also, you can incorporate that. Maybe I'll try to show an example. Now here when you come down, what are the things required, we'll see. So I'm just moving to this regulator. You can see a couple of parameters here. Now reference current, initial position. See, since it's 8 by 6 SRM, every 15 degree we are having a change, means phases are shifted with every 15 degrees. And with reference to first position, I am just turning on and turning off with this angle. So this angle only depends on our logic that people used. Okay, I'll put it. Now what I'll do, it depends on what sign convention that we choose. I can choose 0, 30, 60. The other way possibility is also you can keep this center in terms of having more negative angles and everything. People will take from this side as this also as center. So 0 to 30, the generating mode, and 30 to minus 30 will be motoring mode. Okay, it depends on convention. So now here in that model, what people have considered, so turn on angle as any convention, people can have multiple convention. I think so. This they have used convention from considering from 30 to 30 in a reverse way they have considered. So 0 to 30, 60. Okay. They have considered in this way. I'll let it just they have considered sign convention in that way. This way. So from 0 to 30 negative slope, from 30 to 60 positive slope. So they marked in that way considering this only sign convention. So in this motor they have considered in that way. So when between 30 and okay. So between 30 and 60, if you turn on and turn off, that will give you positive torque, positive current. So that's what the model is mean. Okay. Now if I double, you can see that I'm giving current reference 50 amps. Now if you actually look into this model, I'm just going into the model for understanding. Fine. So this is omega, from where I am getting T on and T off, I am giving on angle, and this omega I am trying to get position. Integration of speed will give you the theta. This is integration, and this is conversion from omega, which is coming in radians to degrees. So you can see the radians to degree conversion will come. After that, this integration we are getting in degrees. So for every 60 degree, I am wrapping the position information. And within this 60 degree, if I take first phase 0 to 60 degree, I am turning on and turning off, I am adding that one, I will get a pulse. So with that pulse, I am giving a signal pulse on and off. T on and T off are coming from here. Now current reference is coming from outside. So I am giving current reference value and I am giving a band control for that one. This is the gate pulse that is going for. I hope if we understand this principle, that is very sufficient. Now let's try to play with current reference T on and T off and see what will happen. Now I'm just running this model. Now you can see at lower speed, when speed was low, okay, we are putting into the hysteresis current and we have referenced the current to 50 amps. So you can see the reference current is 50 amps. Okay. Now as speed is increasing, you can see current reference is maximum side. As speed is increasing due to back EMF, it is entering into angle control. It is entering into, because I am just turning fixed that one, fixed T on and T off. Please understand how I am not varying the torque. I am just leaving that one T on and T off like that only. Fix it for the maximum. So once I fix the current reference, my initial torque is very high. Okay, I am getting the initial torque 100 Newton meter, and as speed increases, you can see after that the torque is also falling by itself. So T on and T off I am fixing and current reference I am changing. Now if I want to change, as we have learned the fundamental point, if I want to change the magnitude of the torque, all I have to do is that I have to increase the current. Okay. Now I try to increase the current and see what will happen. Is my torque maximum is going to come? Fine. Now you can see the current value is increased and torque value is also increased. And you can see the torque value, okay. If the current value, you can see the current value is going at higher current, and we can see more torque is produced, and that is helping us to accelerate. So during this, if you observe right now, the rise is high. So what we can see is that by controlling the current, we can control the required, by controlling the current, we can control the torque. And now I'll put it back to the current. This is for learning exercise only. Now what I'll do is that if I want to make from motoring to generating mode, okay, all that we have to learn is that we have to switch on into negative slope of the region. So what was the negative slope of the region that we have considered? Between 0 to 30 if you switch on, in this case, in this motor conventions, we can see that it will enter into generating mode. So what I'll do, producing negative torque. Okay. Now I'll open and I'll make only changes that I'm going to make the same current, I'm going to make within the positive region. Let me check 5 degrees to around 20 degrees. We'll come back to this point of degrees and everything. Now if you open and see that your torque production is actually opposite. Negative torque, we can see the negative torque is coming here in this region. So You can easily switch from motoring mode to generating mode. All you have to do is that you have to change the positioning of the face, where the position of that one. And if you look to all the faces, you have other three faces on, and as you see that at angle control mode is entering into angle control mode. So I am just seeing the 4-phase current, you can see it here. It is in angle control. Current is already limited. So you can see it is in angle control. You can see that single pulse mode. You can see that current, all the 4-phase currents are there. So they are contributing individually by phases, and this is the resulting torque that we can see. Right? And once we do the outer loop control, and this reference current is going to come from the torque reference. One example we can show which we had. This was from practical characteristics that we had. Maybe more. So here we loaded with the characteristics and everything. So take as no, sorry. This is the outer loop, and outer loop is square root is deciding the current required. Now the torque asked, this was a 4 kilowatt motor, 25.5 Newton was the torque question. So torque at the load, that is creating a reference current here. Now there are actually accurate further, this is actually very basic model of that one is that taking the square root of the torque. But if you correlate and bring actual torque to that one, you will get very good accurate value of current reference in that one. Now I'll try to stop here and show that for this value of this current. So here we can see each phase torque is limited, and the current reference value will decide the torque value. Now if I reduce the torque, if I reduce the torque to half, okay. So let me put some value for 30 Newton, okay. For this lower speed, 150 RPM. Okay. Some issue with the control. The lower speed, proper data we need to build. I'll take my mark. Yes, way back around that. Right. So, this is one of the the same motor model which we had mathematical before. When I was doing 2009-2010 period, we built with a mathematical model. This is the voltage equation, and this is the flux as well as torque equation. And this was the control strategy that was built. 115 and this T on and T off. Okay. We can populate based on the angle required. So this is that model also somewhere we have. That I'll just try to do. So here you can see the phase current energy based on the torque requirement. This is a phase, and if you change the torque value, if you require torque level, I think so we have 12 or 13, whatever the torque, we already mapped that one in the control. Okay, you can see that resultant torque is reduced. So we are getting the resultant torque and current is controlled. This current value is also reduced, can you see? So T on, I reference, T off will decide us the required torque levels. And now coming down to one question that people are asking, and that's very essential to us to learn, is that how do I fix T on and T off based on that one? Now what we can see is that I want you to look onto the ripple of the torque. So the control strategies, people start to look, various people work in a different way. So one of the way is to identify that. You can see this is my current torque ripple. Torque ripple typically we have from 15 Newton meter, it is reaching to 7 Newton meters. Around 7 Newton meter ripple is there. Okay. Now how the T1 and T off angles will help us is that in order to optimize that one, so let's take, if I make it 10 and if I keep it to some more degrees towards 30, I'm going towards 30 degrees, that means I'm going near to 28 or something. See, with this, what I'm area I'm trying to manage, and current reference will be changed by the controller. So if you do that part, and you can see that my ripple is going very high, now 20 Newton meter to almost 7. So the choice of this T on and T off comes with optimizing with reference to the torque ripple or required torque per ampere. There is some advanced controls called as, see, there is a two control categories. One is performance, the primary performance characteristics, secondary performance characteristics. When it comes to primary performance characteristics, we always work on cost, efficiency and everything. So that is primary category of that. The down the line secondary category one based on the application requirement. For example, if you apply reluctance motor for EV, obviously EV application demands torque ripple should be less, noise should be less. In that case, what happens? You have to optimize for that application how much minimum torque ripple has to be there. So during those strategies, secondary performance, you will identify positions, optimize the position such a way that your torque is minimum. And there is other control strategy called as torque per ampere. You should have for less amp, RMS current of less amp, we need to have more torque. that also we have to we can change the values and see. And T1 and T off can be changed as per the requirement. Now, if you do into higher angle control, I think in a higher angle, I made one lookup table. I am not just able to find where did I make that lookup table. So so this is a way of working with low, and I'll try to see that lookup table once, get that one. So you can make all the combinations of required torque and this one in that way, such that you will understand. Or I'll put my tech pieces, that would be. Anyway, I'll show it here on. Quickly, I'll be able to trace for that, but for our convenience, I'll show that. To trace that. Okay, Navya, Stuti, can you send that my thesis that I give? Did I send in my Gmail, not to you? I've sent in Gmail, right? Yeah. Fine, got it. Fine. So just I want to got it. This is my master thesis. I just want to show you what exactly people try and how to do. That will help us. You can see this is the current reference. This is the table. At low speed, what should be the torque and what should be the parameter. And this was the torque waveform. I just saved for you. And we can see that two controllers I have compared. So when stop-known is 35, 33.75 and 56.25. And we also can see that at various angles you will get various torque ripple and everything. So that here you can see the same hysteresis control with different T on and T off. Okay, and we can see the torque ripple in this case is less compared to this one. So we select and we'll optimize. There are these days we have algorithms which have already come mapping with the theta value or T on and T off, where we can get the minimum torque ripple and all that. So this was a fundamental way of doing changing the values of T on and T off and identifying which phase means where we are getting minimum torque. Now, as you go to high speed, you can vary the T on and T off angle to get optimal way of identifying the torque ripple to be minimum and getting the values. And you can frame a lookup table kind of approach. You can see I have made the T on angle, T off angle required, and I have already mapped. Finally, I controlled is in T off angle control mode. So that way we have made a lookup table. So this is a lookup table that we can bring up with reference to change in speed, change in torque, and we can map that one into the model. So we can put that into here when we are considering control of that. This is another example. Can Now, the 2 points that we will discuss is that what we have learned is that by controlling T on and T off, by controlling T on and T off and I reference, we can control the torque and we can control. And T on and T off angle can be selected based on our minimum requirement of torque ripple, whether it's falling within the width. And when it comes to direct torque control or DTC control or control, we are trying to estimate the torque. Getting from this characteristics only, the torque speed characteristics. From that characteristics only we can get back the value of current reference and we can work on that one. So from this characteristics, this people have started to work on that one. For minimizing torque ripple, so what should be the current reference, actual current from this one, and try to optimize the current in that way. So people can work in multiple way to minimize that one. I think I have tried some other exercise also. This way. Another example also again. U-top model. Already there. Torque minimize torque more. Anyway, we can that people can start to work with the torque, required torque levels, required kind of thing. So now let's come back to here. Now, what are the points that we are relevant to EV is that what we can see is that it is a control is if you understand the parameters of torque, parameters of current, and the slope, dl by dt, wave to turn on, wave to turn off, we can easily switch between motor and generating point. This is another key point. Switching from motoring to generating mode is easy. And high starting torque, because torque is proportional to square of the current. Obviously, we can get at low speed only we can get higher torque. And unlike DC motor, it is easy to control in this case. For short duration, you can increase the current. And volume required is this, because there is no I-square or losses within the rotor. It can have more power with less volume, and is economic, efficient, and we can easily switch between motoring and motor. So these are the things that's promising, and ideally it is matching the characteristics of each vehicle requirement. Okay? So that is another key point of reluctance motor. So though again we need to optimize properly with the torque ripple, torque noise, efficiency and everything, but it's apt suitable directly to that one. Other key point is also very essential. If you look at that one, is that we require more constant power region. So for any vehicle, but SRMs are more promising. We can see SRM's speed ratio from maximum speed, top speed, to the base speed. Okay, the speed ratio is high. For permanent magnet based motors, it is 2. For induction based motors, it is 4. And if you see that SRM or reluctance based motors, it is 6. That means what? More region is actually high efficient. And if you actually see the efficiency graph of the system, you can see that you have more region of constant power region with efficiency. Constant torque region is very less. That's what we can see in that. So because of that one, it's applicable. Although there are hurdles of torque ripple, people are well established. Even couple of my works are in that domain. So we have worked on torque ripple minimization and vibrations, also minimizing noise. And still, the challenge is that it's in lapse period. That means it is in not in large production. Any technology from research to the industrial production, if your large production comes, then it's called as close of lapse period. Now, currently we don't have large productions happening research mode, and it is not in large. Research is done. So now we have to look into large production. When it comes, lapse period is over. Now, currently, by the end of another decade, so another decade, we can expect that now few of the manufacturers started to do in India reluctance motors. Now they're slowly increasing. The numbers are increasing very slow rate. Now, if manufacturing comes in large scale, obviously the cost and the availability, it is going to affect, and it's going to reach lesser cost even than induction motor. So that is very promising. Now it's in lab state. By the decade, we have large production. People can start to use this SRM. And already research for the EV application, people have started to use SRM for EV. Okay, there are a couple of manufacturers who already try to build SRM for EV. So that's about the control studies and the couple examples that we can see here. So this was Aspen Bower company, which was in IIT Kharagpur, startup by 4 graduates. So they approached during that time, way back in 2019 or 2020 time. So they approached for this reluctance mode control for EV. What they have done is that they retrofitted into a Maruti vehicle the reluctance motor. And they went with this control strategy of current control based method for that one. So they were able to do forward motoring and the So they were able to do forward motoring, reverse mode condition, all that thing they were able to do easily, and SRM was used. Now that company, all the 4 graduates have been, the company was acquired by other company. It was observed, the idea of that one was putting a reluctance motor into EV. So they have developed and they have executed, and they have been given job offer within the company, and the company was observed with each person being sold out, giving a share of 1 lakh, 1 crore, each person was given. So that's a new idea that people are adopting, even industries also start to work. And couple of other things that people start to work is that reluctance motor they are mounting into the rotor, that is in-wheel drives. So within the in-wheel drive they have started to deploy, and people are working with the axle-based reluctance motor principle. So they are upcoming promising. And now when it comes to pump load application, other one point that I would like to stress is so I just want to stress on the pump load. I'll put it here. The pump load, other point that is very, very important for us to understand control strategy, torque is proportional to square of the speed. So torque is proportional to square of the speed. In this case, what happens is that during lighter speed or low speed region, what happens is that unlike your EV or other motor application, you need to have higher torque, T max at the higher. After that, you need to have control strategy. In this case, we know very well to get T max, we are keeping I reference and it has to be controlled in hysteresis. Hysteresis is needed for this application if you want to have higher torque with this one, and that requires current sensors. Obviously, if you put SRM into an EV application, obviously you have to do current control strategy which can minimize the, which can get the more torque with the, and you need to put current sensors for that one. But interesting point that I have learned and I have observed is that in case of water pumping application, this torque during the starting point is actually low. Okay, and because you don't require low torque in the low speed, and this is at rated speed. Okay, then you know. So interestingly, for pumping application, I felt that easily is that you need not have hysteresis control. So that's what eliminates the current sensors, eliminate that one. All you can do is that T on, T off control, or in case of PWM, what we have used in our case was PWM control strategy. So which was helping us to get zero that one, and we identified that PWM control strategy was helping us very easily in all the parameters that we already looked through that one. So this is very simple to do because for quadratic load, torque requirement is less. So obviously current requirement will fall, your peak current will fall, your RMS current will fall, all that time will be very low. Obviously you have to work with the torque ripple only. So you have to choose T on T off in such a way that it can optimize the torque ripple and it can produce the required torque only at the required speed. Right? So I think so this is another key point when it comes to variable DC PWM technique applying for water pumping system, especially for quadratic and pumping load applications. So this I'm investigating in other ways also. I'm trying to put in. I don't want advanced control strategies for having for water pumping applications. If you put the simplest control strategy, that will be sufficient, and we need not put current sensors, we need not put anything. And also I'm exploring with other kind of motors also for water pumping application that at lower speeds, I don't want the rated torque. Right. So another key point that we can take away. So the model, if at all have seen the model here, you can put the required outer loop, inner loop, and you can explore the control strategies with this model that is available. If you have practical characterization, then you can incorporate those practical characteristics and you can bring into the system. I think so somewhere I have merged a couple of things. It's very difficult to find the files and to show. To one extent, I have showed you what exactly to get. I think so I can wind up at this point. And if you have any couple of questions and if you have anything discussion on this one, I think so that we can discuss both the points. Q&A session we can have. Keep this.
Thank you, sir, for valuable insights of SRM. So, no questions from our side.
Hope if anyone are starting to work on this reluctance motor, if you have any questions or anything, please you can contact me, no issues. and you can use this example. I think so it will be useful for you to understand principles, controls, and there are advanced controls like torque ripple minimization techniques or DTC control, vector control also. But now while in for pumping applications, I don't prefer that vector control is necessary. But when you have EV application, you still can do vector control for this reluctance motors. Okay. So that's from my side, and thank you all. And I thank Nasrima sir for being my guide, my mentor, and I always cherish to be with being at NIT Warangal, doing my PhD. And I thank all the NIT Warangal faculty, Giridhar sir, coordinators, and especially the PhD scholars for coordinating and helping out, for giving this opportunity. And thank you all. Thank you all the audience for this session.
Thank you, sir.
Thank you. Any comment or feedback from your side also is welcome, and I welcome for any interaction. Thank you. Shall we wind up?
Yes, sir.
Thank you.
Good afternoon, everyone. Prashant now will brief idea about his work. He will give you over idea of SRM. He is a research scholar and a Girdhar sir. Much time. He will finish in 10 to 15 minutes.